So great. Hello, everyone. My name is Chris Tiede, and for those of you who don't know me, I'm a graduate student at NYU, finishing up my PhD studies with Andrew McFadgen, and then I collaborate often with Zoltan Hyman and Jonathan Drake. So I tend to think primarily about or simulating binaries embedded in accretion disks, and I think about this problem primarily in the context of supermassive black hole evolution usually. But it's worth mentioning that all of these simulations that I'm going to talk about don't impose any explicit mass scale. So even though we're generally thinking about supermassive black holes, so long as your disk is sufficiently thin compared to the binary, you can draw some conclusions for binaries across the mass spectrum. So just as a brief outline, I'll talk about some of this work that we mentioned earlier, where we found changes in orbital evolution as we go to thinner and thinner disks for these binaries. And then I'll talk a little bit about some results from our group on this eccentricity driving from gas disks. And then I'll finish with some dynamics of accretion using tracer particles. Okay, so for starters, if we're thinking about these massive binaries embedded in accretion disks, what exactly are we thinking about? Well, we tend to think about kind of compact, late-stage supermassive binaries where there's been some galaxy merger and these binaries have come together and they've managed to shrink their radii down to a parsec or less. But this is before they've actually formally entered a gravitational wave emitting regime. And then as far as the gas, we imagine the gas coming in with some angular momentum. We think of it as optically thick so that it radiates away its vertical pressure support and flattens into a geometrically thin accretion disk. And then we care about this because kind of the point of this is this gas can influence the orbital evolution of the binary via gravitational torques, as well as the direct accretion of both mass and angular momentum. And then this gas can also give us a channel for the actual electromagnetic observation of these compact, massive binaries. So when we simulate these things, we have to make some parameter choices about how to do this. And kind of typically in the literature, there's kind of emerged a model that many people have used to compare against each other. So some of these choices we have to make are first we put in some viscosity into the disk, and that's typically given by this alpha viscosity prescription, where this dimensionless parameter alpha tells us something about the characteristic speed and size of kind of subgrid turbulent eddies that are giving us angular momentum redistribution. And we wrap that up into this nu that goes into our Navier-Stokes equation and gives us angular momentum redistribution. This disk is also kind of in this classical or historical model treated as isothermal. So P here is the vertically integrated pressure of the disk. Sigma is the vertically integrated density of the disk. And then the sound speed for these thin disks is proportional to the thickness or the scale height h of the disk. So then the last thing we have to choose is we have to actually make a choice for what the thickness or the scale height of the disk is. And it has been typical for people to use a value of this of about 0.1. And additionally, in this kind of thin disk picture where h over r is small, it's worth mentioning that h over r is inversely proportional to the Mach number of the flow in the disk. So when you do this, oh yeah, and it's worth mentioning for those who aren't as intimately familiar with the problem, you get kind of, this shows kind of the characteristic structures that you get when you do this. So the binary carves a deep depleted cavity, but this cavity is typically kind of lopsided, and there's a density lump that forms that goes around with a frequency of about once every 5 binary orbits. Each of the binary components tends to develop its own circumsingle disk, and this is what we refer to as these mini disks that have been discussed quite a bit so far. And then there are these streams that form that connect the binary or the outer disk to each of the binary mini disks. So then studying the orbital evolution of this in the last kind of 3 to 5 years, people have started to kind of converge on a picture of what happens to the binary. And what they find is that the disk is actually giving angular momentum to the binary in this picture, and so much so that it's actually driving the binary apart. So if we're thinking about these kind of late stage compact massive binaries that could be either LISA sources or PTA binaries, the presence of this gas driven phase could actually inhibit the binary from getting down to small enough separations to emit gravitational waves and potentially merge. But among the many caveats to this kind of fiducial historical model, one of them is this kind of characteristic scale height that we choose, or the Mach number of 0.1 or a Mach number of 10. is not particularly appropriate if we're thinking about these compact, massive binaries embedded in thin AGN-like disks. In that case, we would actually expect this disk scale height to be something like 10 to the minus 2 or 10 to the minus 3, so Mach numbers of like 100 to 1,000. So in order to see how this changes our picture, I did a study where I systematically considered higher and higher Mach number disks or thinner and thinner disks, and to see how that would change the orbital evolution of the binary. And we found that it did actually have a significant effect. So on the right here is showing the specific angular momentum gained by the binary per unit accreted mass. And the important thing is if you take the average of these time series and convert it to a change in the binary separation, you find this plot that we looked at earlier, where for these comparatively warm and thick disks at Mach 10, maybe I'll see this pointer. So these comparatively warm and thick disks at Mach 10, we recover this picture of the gas giving angular momentum to the binary and driving it apart, causing it to outspiral. But as we go to thinner and thinner disks or higher and higher Mach numbers, we see this monotonic decrease in the binary migration rate, such that it changes sign at about, in our case, a Mach number of 25. And then if this were to continue all the way out to the Mach numbers we expect for these AGN-like disks, then this would kind of recover this canonical picture of the gas removing angular momentum from the binary, shepherding it closer together towards a gravitational wave emitting regime and potentially towards merger. So one of the things we might be interested here is what is actually changing that's causing this. So we can break this migration rate into that due to the direct accretion of mass and angular momentum. So that's this dashed dotted line. It doesn't seem to be doing much. And then also the change in binary migration due to the gravitational torques in the binary disk. And that's this dashed line that seems to track the total. So something is changing about the morphology of the disk that's giving us different gravitational torques and changing the sign of the binary migration rate. So in order to understand what's going on, we broke the disk into 3 separate regimes. There's the innermost disk that has the binary components themselves and the mini disk. This region called that we call the cavity region, which includes the inner edge of the binary cavity and the streams, and then the outermost disk, so the rest of the circumbinary disk. And this is a plot showing kind of this mini disk problem that we've argued about a little bit so far, where we find that from the torques for these warm and thick disks in the cavity region and the outer disk are generally negative, but you actually get these strong positive torques from the mini disks. So in this comparatively warm and thick case, these mini disks are dominating the net torque and actually causing the binary to expand. But as you go to thinner and thinner disks or higher and higher Mach numbers, you find that the torques from the mini disks don't change a whole lot, and nor do the torques from the outer circumbinary disk. What's really changing is you're getting these increasingly negative torques from the cavity region. So we can understand this if we look at time average maps of the surface density and the torque density in these disks. So we see that we can understand why we get negative torques from the cavity region, because this cavity region for all of our Mach numbers has this kind of characteristic time average shape that looks kind of like an egg. So it's kind of like this ellipse that's rotated a little bit, where the far edges of this egg extend into these green quadrants of positive torque, trying to spin the binary up. And the near edges of this egg extend into the quadrants of negative torque. And so because the material trying to torque the binary down is slightly closer, we're getting these negative torques. And then as we go to thinner and thinner disks or higher and higher Mach number, what happens is the disk actually starts to pack more and more material into this characteristic egg shape, giving you stronger and stronger negative torques, and eventually switching the sign from positive and binary out spiral to negative and binary in spiral. Yes, okay. And then it's worth mentioning that there have been a number of more recent works looking at kind of the similar picture of how does the binary migration rate change as we change the thickness of the disk. And the general story for all of these is that for generally warm and thick disks, at some point you get binary out spiral, and then as you transition to colder and thinner disks, eventually you recover a picture of the gas removing angular momentum and leading to binary in spiral. And you can kind of move this critical point around about where this turn actually happens by varying things like viscosity and the mass ratio and things like that. But for all of these, they do find that at some point you hit this critical point and get binary in the spiral. Okay, so going back to this kind of fiducial model, we talked about how considering thinner and thinner disks transitions you from this picture of out spiral to picture of in spiral. But another thing that we could potentially relax about this model, among the many things that you could change, is that you could no longer fix the binary on circular orbits. So this has been done, had been done in the past for kind of limited eccentricities, where for small eccentricities, people found that you get eccentricity driving, and then for some of these larger eccentricities, you actually find eccentricity damping. So we did this in work led by Jonathan Drake, where we looked at a broader set of eccentricities, and we found this interesting curve that had most notably two equilibrium points. So like we mentioned before, binaries that start with a very, very small eccentricity are driven back to circular. But any binary that starts with an eccentricity greater than about 0.1 will be driven to this stable eccentricity point for our simulations that came about at about 0.45. And then almost concurrently with this, Dan and Paul found this very similar result where they found kind of circular binaries, or really small eccentricity binaries get driven to circular, and then any other eccentricity gets driven to the subtractor point at about 0.4. And in both of our cases, we found that the average change in binary semi-major axis, either at the stable eccentricity point or as the binary oscillates around it, causes the binary to be shrinking its semi-major axis. And that's even for this comparatively warm and thick case of a Mach 10 disk. And then it's worth mentioning that this stable eccentricity of 0.4 or 0.45 is kind of astrophysically interesting, at least here. If we're thinking about LISA sources, if they undergo some gas-driven phase in their evolution and they're driven to this equilibrium eccentricity, if they start their gravitational wave emitting from this equilibrium eccentricity, they'll retain enough eccentricity upon entering the LISA band to actually have that eccentricity be detected. So there could potentially be signposts of a gravitational wave, or sorry, of a gas-driven phase in the gravitational wave signal of LISA sources. And then additionally, as I think this is a plot that Zoltan has mentioned a couple times, where we looked at the eccentricity distribution of these post-AGB stellar binaries, and it has this kind of suggestive bimodality where there's a number of them with low eccentricities, and then the second peak at eccentricities of about 0.25 or 0.3 that could potentially suggest a gas-mediated eccentricity driving. Okay, and then the final thing I talk about is more of kind of a dynamics question of how these binaries actually accrete, so the actual process of mass transfer across the binary cavity, where the motivation is when people first began studying this problem, there was some thought that the centrifugal barrier from the binary could actually prevent mass from crossing this cavity and getting onto the binary. And while from 2D simulations, we know that this is not the case, that mass gets through the cavity and onto the binary, this cavity structure is still very chaotic and complex, and this process is not super well understood. Oh yeah, and in order to do this, I put Lagrangian tracer particles into our Eulerian hydrodynamics code so that we can follow the hydrodynamic history of fluid elements as they move through the disk. And when we did this, we found a number of interesting things, but two of kind of our main conclusions can be given by these characteristic radii, where the first is what we call an accretion horizon. So if you consider some crossing radius, and all material that crosses that radius at some point, what's the distribution of radii at some later time? And as you shrink that radius down, eventually you find a radius where all material that crosses it, none of it escapes back out. And for us, that happened to be at about 1.05 binary separations, shown here, where all material that crosses it empirically never escapes back out to the cavity wall in the circumbinary disk, and is destined to be joined to a mini disk and eventually accreted by the inner binary. And this is a little bit interesting because it lends some credence to why early simulations that actually excised this innermost region with the binary got pretty good results for measuring kind of torques from the outer disk and the structure of this outer disk without including these mini disks in their simulations. And then lastly, for this last one, we found that if you look at all accreted fluid elements, almost all of them become gravitationally destined to join the mini-disks in the binary about one binary orbit prior to actually joining a stream and moving across the cavity. So here, just in these time series of quantities, the blue curve shows when, if you integrate a fluid element forward from its phase space coordinates that we have from the tracers, it's not sufficient to cross the cavity and join a binary mini-disk. But the time series switch to red when integrating them forward in the circular restricted three-body problem becomes a sufficient condition for actually moving that material across the accretion horizon and within a Hill sphere of one of the binary components. And we can understand this by looking at n-body simulations of concentric rings around the binary, both initially circular and initially eccentric, where the tidal deformation of these rings at close enough radii actually creates these streams and moves material across the accretion horizon and within the Hill sphere of one of the binary components. So gravity is what's doing the work to actually move this material across the cavity and onto the binary. And then the role of fluid dynamics here is in the outer disk to remove angular momentum from the fluid to get it close enough to be tidally captured. And then also in the mini disks to actually break the ballistic trajectories of fluid elements in the streams upon hitting the mini disk so they can be subsumed into the mini disk and ultimately accreted by the inner binary. So I guess maybe I'll put my conclusions up there and see if anyone has any questions.
Okay, there's so many questions. While people get to the junior people who have questions, I want to ask you a question.
Okay.
So you kind of dropped gravity out of thin air for me. I didn't realize where the gravity started or like when you turned it on. I was expecting, that gravitational was to be really important if you're at an R over A of 1 or 1.5. So can you talk a little bit about gravity and when you added gravity in the last slide?
In the tracers? Oops.
Maybe I misunderstood you here. So, of course, I'm interested in gravitational waves.
Mm-hmm.
But you didn't talk about gravity before or like adding any kind of gravitational wave emission component to your model to shrink the semi-major axis. Did I misunderstand?
There's none of this.
There's none of that?
No, sorry.
But they're so close, right? And so what do you mean by gravity?
Gravity.
Like Newton.
Oh, like Newtonian gravity. Yeah, sorry. Like integrating particles forward in the purely circular restricted.
Newton is getting
problem.
a lot of airtime at this meeting.
Yes.
And I feel like Einstein is a bit upset. Okay, fine. Thank you. All right. Now that I've asked my naive question, are we over here?
Yeah, if I'm not mistaken, Einstein's birthday just passed, so I'll represent him on Thursday with similar movies.
Very kind of you.
I'm not sure I've seen the movie and noticed this before, but something that I don't see in mine, and so it caught my eyes. If you can go back to the movie.
Which one?
The movie on the prior slide on the left. Yeah. So coincident with the inner circle, it looks like there are these discrete structures that they'll accrete, pass across, and then go back, and then cause a break of the stream at that radius.
Mm-hmm.
And because I don't see that in 3D, I wonder if it's an effective 2D, and I wonder how important that is for basically the outer edge of the disk and how much material goes back out.
Interesting. Yeah. So you're talking about this apparent stream breaking here.
Yeah.
So that's interesting. I would love to talk about that more because I feel like I've always kind of seen that, and that was what got me interested in this question.
Okay. Yeah,
because I was trying to identify the spot of where these streams are actually snapping, and looking at at what point is material kind of joining the mini disk and which material is being flung out to the cavity wall and escaping back.
Yeah. So is that breaking point quantitatively connected to?
Yes, I think they're essentially the same point, that this horizon is the kind of the breaking point.
Okay, we should talk more about it.
Yeah, but I would be curious to see the 3D version. Yeah.
That is very cool. Okay.
Yeah, very interesting work.
Could you say your name for everyone on Zoom?
My name is Bhupendra Mishra from Los Alamos National Lab. My question is that what happens if you fix the disk height but change the alpha viscosity parameter, because the alpha is like 0.1 here. And if it comes from the turbulent MHD models, let's say, getting an alpha of 0.1 is extremely difficult.
Getting a small alpha is difficult.
Right. So keeping the disk height fixed but decreasing the alpha to 0.01, will it change anything?
So if I understand you correctly, you're asking about in the mock study about fixing viscosity, fixing alpha at different values versus fixing at much lower values. So I don't know about small values. So something I actually swept under the rug to keep things simple is that we actually did that study at fixed fixed kinematic viscosity, so to keep our viscous times similar. So this is an additional plot. So this is the same thing. This is L dot over M dot, but this is the transition point. So we did this at fixed new viscosity. So that means that alpha was actually varying in those simulations from about 0.1 up to something a little greater than 1, which we could debate later if someone wants. But we also repeated the simulation at constant alpha. So we fixed it to 0.1 and we ran for the appropriate viscous time. And we found this red line, which was almost the same behavior. So I don't know if that answers your question, but. Okay. I'm sorry, I'm struggling to hear.
Getting such a large alpha from turbulent model is very challenging.
Yeah, so we could, so for these constant nu, you do have large alphas for the higher Mach numbers.
The question is comparison with MHD circuits.
Oh, I'm sorry, I never heard that. Okay, my apologies.
Hold on. Let's let Chris try to answer.
Okay, so yes, I would be very interested to hear from Julian, actually. Yeah.
Okay, wonderful. If you want to pass it to Julian, that's great.
The answer comes in two parts. The first is that in global simulations with MHD, inside the disk body, where comparison with alpha makes sense, the typical numbers people find are not particularly small, more like a few tenths or so. But the second is that alpha breaks down badly wherever there's a gradient, and in particular at the inner edge of circumbinary disks. So in fact, it's not constant at all in that region, and tends to be, if anything, larger than typical at that edge.
Okay, thank you, Julian. We have a question on Zoom.
Yes, Roman.
You're muted.
Just to ask Sally.
Hi, Roman. Would you be able? Did you have a question? Would you be able to unmute yourself? Oh no. Okay. His hand is up.
Is it no question, or you can't unmute yourself?
He wants a high five. Yeah.
Can you type your question in the chat? No. Okay. That seems.
While you try,
We'll come back.
Sorry. Yes. Okay. Suddenly, sorry. My apologies. My machine, for some reason, just totally froze for, I don't know, like a minute. So I was struggling. Chris, thank you very much for a beautiful talk. Can you please show that breakdown of the torques that you were demonstrating? You know, like the inner cavity and so on.
This one?
Right. So basically, the main, I mean, looking at this figure, it looks like the red curve, which is inner part from this, interaction of binaries with components of the binary with a mini disk of the opposite component, is whatever is causing the expansion of the binary, right? I mean, primarily. Is that the correct understanding?
I think so.
Right. So in that case, I have a question actually not to you, but to
sorry.
Don't lie if he's in the audience, because I believe the first claim of this orbital expansion was done in Miranda et al. In 2017. And in that study, the inner region was actually excised. So there was no modeling of mini disks, as far as I understand. I mean, it was then confirmed with, by studies by Diego Munoz and so on. This basically the same authors, Dong Lai Ryan Miranda. But I'm wondering how was it possible that not inclusion of this mini disk still led to this orbital expansion in this previous work by Ryan Miranda in 2017.
And I'll also add that this most recent work by Penzlin and Klee also excised the innermost region and was able to get this out spiral. And it seems to be that if you keep very good track of your angular momentum fluxes through the disk and what's crossing through the inner edge, kind of this argument of you get conservation of angular momentum. So if you're delivering enough angular momentum through that inner boundary and you keep good track of it, you can still get this out spiral. So when we're including the mini disks, we're getting angular momentum passed through wherever this inner boundary would be. And in our situation, it's being maybe redistributed between gravitational torques that are acting on the binary and some angular momentum that's also accreting through the holes. But ultimately, all that angular momentum that goes through that inner boundary has to end up on the binary somehow.
I see. So one has to take into account the kind of the flux of the angular momentum through the boundary when doing this calculation.
I think so. I think it's kind of this powerful angular momentum argument, but kind of a somewhat curious thing that you do get the same result with the X-size binary if you're careful about your angular momentum fluxes, or if you're summing up torques from the full disk, including the mini disk.
Okay, thanks.
Says that once matter gets inside a little bit more it's definitely destroying light.
Which means that no matter what happens to it when it's inside that radius, whatever angular momentum change it has, positive or negative, is just given right back to the binary when that fluid element joins the binary. So I've long wondered why you bother sort of dealing with that inner region, because it's unnecessary. I think in part we didn't know, but also.
Okay.
Are people waving? Oh.
No, so you should finish your thought.
Okay.
Yes, absolutely. And then we're going to go to Don Lai, and then we're going to go to Alberto.
So I think for circular binaries, it might turn out that it is okay to do this because that angular momentum can only go to the shrinking or expanding of the binary. But if you're thinking about eccentric binaries, I'm not sure this would hold. And it might be more complicated. But I'm also not sure that this horizon holds as we go to more eccentric binaries and with different mass ratios as well.
Okay, go ahead.
For circular binary, the reason you can cut off the cavity that works is because there's very little feedback from the inner region on the disk. So as long as you try to do this very carefully, imposing well-defined outflow boundary condition, and you can get good answer. Okay, but for eccentric binary, that's not the case. But I have a different question. So I have a different question, just quickly, right? I think one of the reasons pre-2017, there are all these claims of migration inwards. It's because a lot of these things, they basically find the transient phenomena, basically did not really relax the disk sufficient long time, in addition to some other sort of hidden mistakes, I think. So my question then is, to what I understand what you told me is that this simulation, what you did is most of this one is basically done for torus, right? Finite disk.
Yeah.
Right. So I guess the question then is, to what extent you are finding sort of quasi steady state behavior rather than some kind of transient phenomena, given the sort of earlier lesson people should have learned, I think, hopefully.
Yeah. So what we regarded as our condition for quasi-steady state was looking at these signals of specific angular momentum gained per unit accreted mass. So we looked to see that we had many hundreds of orbits of a fairly constant signal of angular momentum being given to the binary. So that was what we did to consider this quasi-steady state. And this was mostly based on the notion that you get the same answer from a finite torus as you do for an infinite disk from your work in terms of this accretion eigenvalue.
Okay, so we're going to go to Alberto, and there's a final question on Zoom, then nothing will keep us from coffee.
Right. So, well, going back to the mini disk, right? So, I mean, there is a good point that whatever angular momentum you cross to the whatever excision region you have, right? If you're not missing what flunks back to the disk, that's going to determine the evolution of the binary. So, for circular equal mass binaries that also remain also circular, that's obvious what the binary does, right? You just have to compute that. For eccentric unequal one, of course, that angular momentum can go in mass ratio change, eccentricity change, orbital evolution, orbital, major axis change, right? So it's not obvious at all that you can, in this case, you can ignore the dynamics of the mini disk because, how the matter is distributed between the two holes is going to matter in, how this angular momentum changes the different orbital elements and components of the binary.
Mm-hmm.
Okay, thank you. So was that a comment? Did you have a question?
I agree with Roberto, yes.
Okay, you agree. Awesome.
Do you agree with that?
Yes, I do.
Okay. All right. Jeff Ryan.
I had the same comment. Alberto covered it better than I. That was a great talk, Chris, and enjoy your coffee break.
Great. Thanks, Jeff. It's good to see you.
Okay, let's thank Chris again.